Joshua H. Tyler. I'm a recent PhD graduate here at UTC. My advisor is Dr. Donald Rising. This project was done in partnership with TBA, EPRI, and GPA. So that's Anthony Murphy at TBA, Thomas Cook at EPRI, and then Christopher over at GPA. And this is enhancing power grid reliability with real-time edge compression. Here's just a quick overview of how the session is going to go and into our introduction. So our critical infrastructure is dependent on electricity. So like right now we're using electricity for like lights, the presentation, HVAC, elevators, everything requires electricity. So it's pretty much like the critical thing that we need to protect and make more reliable. So one way that we do that is human monitoring and then automated monitoring. Human monitoring is really expensive because you have to train the people to monitor it, and then you have to hire them to look at the data, and there's way much more data than humans could possibly look at. So then we try to automate that. The issue with automation is that we record a whole lot of data. It generates about 2.7 petabytes of data per year, and then like we have to like create an approach that's able to parse through all of that data and then be able to make some kind of intelligible action out of that. But true reliability does depend on that automation. So we need a way to be able to quickly compress that data and then also analyze that quickly. So an operational overview, we have our power generation over here. That generates power over these different substations, and then the power at these substations are recorded by something called a digital fault recorder that measures the voltage and the current going through it, multiple channels. So right now what's happening is the data will be recorded, and then in 14 days, it's automatically deleted. So we're losing, we don't have more than 2 weeks worth of history on our grid right now, unless there's something really catastrophic that happens and a technician goes out there, pulls the hard drive, and then stores that back at the headquarters. But that also takes a cost because that requires the logistics of someone going out and getting it. So in order to really get actionable information, we need to be able to compress it. So Thomas Cook over at EPRI came up with this idea called the cyclic histogram, where you take all the data in as you record it, and you generate a histogram of that waveform as you're going on. So in the top left, we have an example of that, where we have this nice little sine wave that at this fundamental 60 hertz that power is distributed at AC. And then on the top right, it's called a residual histogram, where you take the data in, and then you subtract what it should look like. So there's an ideal signal that should of what you wanted it to look like. You subtract that out, and then you get only the distortion data, which highlights like the unintentional potential fault behavior that's going on. So that's pretty useful for identifying faults, because you're looking at what shouldn't be there. Then on the bottom left, we have a fundamental frequency. We have a frequency histogram. So all power in North America is transmitted at 60 hertz AC. I know in Europe it's 50 hertz, but I'm a fan of 60 hertz. So we're able to, in this histogram, we're able to see how the frequency of the actual transmitted data deviates either above or below that fundamental frequency, and then we can also see if it's in with a tolerable safe operation range. And then on the bottom right, we have the RMS histogram, which is essentially the total energy that we're transmitting. So if we know we know what a certain bus is rated for in terms of kilovolts, so then we can read that data in and see like how far or below that's skewing. So in order to implement that, I used Python. The issue with the great thing about Python is that it's really low level for people to get into. It's pretty simple for people to look at. There's not a bunch of memory management and data type management. The downfall of that is it's slow compared to something like C or C++, because Python runs line by line, whereas C++ compiles. So there's at the time, I think this was 4 or 5 years ago, there was a new library that came out for Python called Numba, which allows LLVM compilation to pretty close to machine code. So it's not exactly as fast as C, but it's a lot faster than Python. It's up to like 100 to 1,000 times faster than Python. That it allows just-in-time compilation and then caching of those next functions. So then when you recall that function that has the JIT header on it, it's able to call that compiled function rather than recompile it. In order to get the data in, especially for the cyclic and the cyclic and the residual histogram, there had to be a time synchronization going on. So I had to use some signal processing to kind of estimate where the cycles were starting and then get them all on the same time scale. So then we could be able to see it on this histogram scale. And then frequency histogram interpolation, there's a really neat function called the fast Fourier transform in order to get the frequency content out of it. But that function was too general for our specific range of frequencies that we wanted to observe. So there's, in the spirit of doing compilation and then looking up, I compiled the FFT in a very small range and then just simplified it to a matrix operation instead of an expensive trigonometric function. That sped things up quite a bit. So then we tested it. We tested this functionality looking at capturing or compressing data in different time intervals. So we tested it doing it in 60, 30, 10, and 5-minute intervals. And the amount of time it takes to run these functions or generate these histograms out of the recorded data kind of scales with the amount of time that you're taking the observation over. The 60 minutes data is the longest time it will take. And we were able to see that it ran in less than a second per line of data. So you can record for an hour, and then in less than a second you'll have those histograms generated. And that was on really old hardware. So when TVA came to me with this problem, they were like, "Yes, we need this functionality, but it has to be able to run on these was it like i5 fourth series CPU, so it had like 2 cores and maybe like a few megabytes of cache on them and 8 gigabytes of RAM. So it had, and they said not only that, it had to be able to run in a way that didn't interfere with their current operation. So these these machines were already stressed enough having to run the continuous monitoring and recording, and then on top of that, they wanted this new functionality. So to be able to implement a new functionality like post 2020 on an old machine with only 1 second is pretty interesting. Okay, so then looking at data storage requirements, the original file size from a single DFR in different cases, like at worst, was 41 gigabytes, and then uncompressed these histograms captured at 60-minute intervals took up only 65 megabytes per day. And then when taking recording all these histograms as binary files and then zipping them up using WinZip, it took up only 4 megabytes per day. So just imagine that going from 41 gigabytes a day requirement down to 4 megabytes a day. So we got the compression stuff. Pretty much figured out. Next is the analytics,
What was the compression thing again? Like, you just regularly, like, what compression algorithm did you use?
It was just Windows zip.
Oh, and that was...
Yeah, it's not gzip, but it's like, what is it, like Huffman? Oh, Lempel ziv.
Okay, not familiar with that one.
Yeah, it's just Windows default zip compression. So it's no specialized compression. It's a generalized compression method. So the OSG files, or the original raw recordings, are just binary files. So you load those into Python, generate the histograms, and then spit out the histograms as binary files themselves. And those spit out binary files at the end of the day. So this was 24 different intervals, took up 65 megabytes. And then taking those output binary files and then zipping them using Windows default zip, it turned it into 4 megabytes. So what was that, 10,000 times less data, which is good. So in terms of cost, we were able to take that down from 2.6 petabytes of data down to less than a terabyte of data for a year's worth of data. A year's worth of data taken from the distributed power. So imagine it's like there's some data people in here taking a 2.5 petabyte storage solution and then being able to store that on something the size of a gum stick. Okay, so next, we've got the compression figured out. We need to make sure that this data is still usable. So we're fortunate enough to get some examples of some fault data from TBA. So first, there's a CVT event that can unfortunately lead to like really disastrous results, like explosions of substations that can, one, cost hundreds of thousands of dollars, and two, unfortunately, lead to the loss of life. The next was a voltage arcing event caused due to a loose connection somewhere in the substation. And then the third case was just an issue with faulty DFR firmware. So there's different ways to be able to analyze this. With the cyclic and the residual histogram, we could do cross correlation between a known event and then data as it's streamed in. And then there's vector-based metrics, which are pretty bog standard. The variance mean, or the PMF, the probability mass distribution, like threshold outside of a given tolerance, especially for something like the frequency histogram. And then, so if you notice, there's no AI going on in this all the time. So people on the utility want something explainable. Especially if we're using this to guide some kind of reactionary response. We want to make sure that any time that something's flagged as potentially problematic, we can go back and see why it was flagged as potentially problematic. If we throw it into something like a classifier, machine learning makes its own decisions, but it doesn't necessarily share how it makes those decisions. But if we use something simple like the variance or mean, those are the things that we can go back in later and then see exactly how those were calculated. Okay, so in the first case, we pretty much get the same results regardless of the interval that we use. So we were able to pretty much just say, okay, we only really need to calculate every 60 minutes, and then that reduces our overall file storage. Here in the CVT event, we were able to get something, I think about like 8 minutes. We were able to see a flag of the likeliness of an event happening 8 minutes before it happened. So we were able to pick up that behavior and then throw a flag. So either like shut off a system so it doesn't have a fault, or bring in a technician and they can take preventative measures. Then in the case of the arcing event, we see the variance of the RMS go pretty wild in all of the cases. So a lot of this kind of looks noisy when you take it at shorter and shorter intervals, which makes it a little less predictable. But when you take it at the 60-minute intervals, it looks a lot smoother, except for like here, I think like 7 hours before an actual event happens, we're able to set a threshold to say, okay, it's pretty likely that this event is going to happen. We need to send a technician to go loosen that up. Here in the DFR sampling error, we were able to see that the frequency was like not anywhere near to where it needed to be. So like on that first time that histogram calculates, we would be able to see, hey, there's something wrong with how this thing is being monitored and recorded. We need to send a technician out and make sure that it's being recorded correctly. Okay, so in the 3 different cases, we were able to see the CVT up to 2 minutes before something happened. We were able to see the voltage arcing 6 hours before it happened. And then we were able to see the DFR sampling issue immediately after it took the first recording. So that wasn't necessarily a fault, but it was a potential for error because we weren't we weren't monitoring the power correctly. The overall memory used to calculate this was less than 131 kilobytes, so that's good. We were also able to process it. All the processing took less than 6.19 microseconds, so a pretty instant response to see how your system's doing. Okay, so our conclusions. So it was a computationally efficient implementation of the power generation, or the power histogram generation. Took less than 7 microseconds to detect a fault. We reduced the data by 99.99%. 99.96%. We took the storage down from like $100,000 to $40 a year. I don't know if anybody's an accountant, but it shouldn't take an accountant. Yeah. Yeah. So like, yeah. So we had different lead times. So we could take an automated approach with 2 minutes worth of warning, and then a human-based approach in 6 hours, and then we know the DFR sampling immediately after we took the first recording. And the great thing about this is it's open source under an open BSD3 license, so anybody can come, anybody is able to come and then download this and use it on their utilities, granted that they're using the digital fault recorders. So someone like, you could take someone from like a third world country that doesn't have a lot of money, and they may have some kind of hardware, and then they would be able to download this for free without even having to contact us, and be able to use it to monitor their own grid and then store a large library of data over the years. All right, any questions? How much for
Are
time?
you somehow marketing or exposing this to utilities from third world countries so they can find it?
Not right now. So we're still kind of going through long-term validation with TVA. So TVA has started to adopt it into their fleet because it's so it's out of the way, and they can just start doing it. So they've started to adopt it, and then unfortunately we have to kind of wait a couple of years for the library to build up, and then once we have that library built up, in addition to the event logs with faults, then we can start saying, okay, then we can start looking and seeing if we can do fault prediction, and then if we can actually start doing like large-scale fault prediction and automated approaches, then we can say, okay, yes, this is a solution to be able to prevent faults across the system, guaranteed. And then we can start marketing it for real. Yes?
What was and sorry if you already said this, what was the frequency of like the interval of your reads on the data?
60 minutes. Oh, so we were sampling at 960 hertz.
Okay, gotcha.
960 samples per second.
So, did you look into, I don't know if it would be any better or not, but using columnar data, specifically storing it in like per key files, because I know I was doing a data pipeline and the compression on that stuff is ridiculous. And with time series data, it actually works really well.
Yeah, the question is, does it store the data in a way that we can do fault prediction?
Right.
And does it get better than 99.96%?
As far as like retaining it, the data?
No, I mean compressing it at the end of the day. Have I reduced my storage requirement by 99.96%, in addition to not requiring new hardware?
Right.
Because like this was doing it in a second.
Yeah, so I know it's extremely efficient, and I'm only speaking from, like, you would have to actually run it on the data to see, right? But like, speaking from my own experience with it, like, I thought that I was messing up with the amount of compression it was giving and how quickly it was doing it. Like, this can't be right. But then I would, isolate it, uncompress it, and everything would be there, and I'd be like, okay, I guess per key is just really amazing.
Yeah, could you send me an email with that?
I can't. What's your email?
I wrote it up there.
Yeah. Also, I'm going to have to look into Numba, because that is awesome. Did you look into PyBind 11 at all?
No, because I was like, it was just on one of my YouTube scrolls, and someone's like, make sure as you do, because like my YouTube is very, yeah.
So PyBind 11 is a way to do bindings into C++ code. It's a Python library, and I've used it before whenever I've had to make custom CUDA kernels that have to do like really, really fast parallel operations.
Yeah.
You can use PyBind 11 to call directly the C++ functions, and it's an interface between Python and C++ as a language binding.
Interesting. So you essentially call it in Python, and then so it's like just expanding the definitions into C++ functions.
Sorry, say again?
So it's like expanding the list of definitions that you can call in Python to the definitions.
Yeah, so you have to write Yeah, essentially you can have a C++ compiled application, and with PyBind 11, you can you have an interface into that, so you can yeah, you call it from Python, and you can pass it parameters, and it will basically call that within the compiled C++.
Will it automatically vectorize for loops? Because you said for CUDA, and like that tickled my ear.
Yeah. So I guess I don't really understand the question. Like, what do you mean by automatically vectorize?
Okay, so is there a marker?
You got one?
And it's great because it's green because I can use that for NVIDIA. So let's say that I have an array.
No, I'm taking them back, Josh. Good old days.
And then I want to run a for loop that calculates y. So I just say for I equals 1 to length of x, I say y equals y plus x of I. And I'll just say y equals 0 here. You're good coders. And then the way I would vectorize it on something like CUDA is I would say I would add x of 0 plus x of 1, and then I would also do in parallel
Yeah, I think
x
what
of
you're
2
saying,
plus x plus 3.
So
And then I would take this result and add that and get y.
yeah, so you would want to contain that all within the CUDA kernel itself, as you call it. With PyBind 11, you could potentially do that with. I mean, you could do it with Python code, but you're losing the efficiency there, right? So you
Right.
basically want to, with PyBind 11, you would want to give it the entire array and whatever other parameters you need to tell it what to do, and then call that C++ function to do it, and write the C++ function in such a way that it would do the vectorization for you within like as it's loading up the CUDA kernel.
Okay.
Yeah.
Like, I'd like something that just automatically does this because I have students that write code. I have students that write code that's inefficient that like I have to go in and then check. Like I write good code, not egotistical, but like I've been doing this for like 10 years. So like, and I love using parallelization. So like anytime I can vectorize, I vectorize. But I've got students that will use for loops for like the weirdest stuff. So if I can just like call some kind
and
of
to
compiler.
be fair, PyBind 11 might have something like that. I have not like done like the absolute deep dive onto it, but whenever I used it, it was really just I write all this stuff that I need in C++ that I need to run there, and I just have one interface, with like the functions, and they take all the parameters they need to even do stuff that I, very expensive interfaces for the functions.
Interesting. I'm sure it would love like NumPy functions and NumPy arrays.
Yeah, and I mean, well, with NumPy, you wouldn't really have to necessarily do that unless you specifically wanted to run it in like CUDA, because NumPy is C behind the scenes. So I don't know. I mean, that's stuff that I would have to like get down and run tests on to see like what the performance gain would actually be. Just thought I'd throw that out there if you, and I'll send you an email too.
Okay.
All the stuff.
So I'm assuming that TVA are very pleased,
Yes.
since you've got it without upgrading any hardware.
Right. They have this brand new functionality. That's like, I think, like it's even better than what Oak Ridge has right now, which I thought was wild because I looked at their public library because like the idea was twofold. It was one, to be able to do fault prediction, but two, to be able to generate a massive library of grid event data. And there's no one in the world has like a 24-hour grid operation library out there because it's too expensive. you'd be generating 2.6 petabytes of data every single year just to store the data. So like not only the data storage, think about parsing through that data. So you'd have to have like a file system on top of a file system in order to parse through all of that.
So a big part of it is realizing we don't need the granularity, of every 5 minutes. We can roll out to 60 minutes and still get the same exact results.
Right, because it all shows up in the distribution. Because the distribution contains even down to the the 5 grain, 5 minute information in there. It's just also included in addition to all the other 5 minute interval data within that 60 minute interval.
Do you run into a lot of errors with decompression?
No.
I noticed that can happen often with Windows.
No, I didn't. No, because I took it off the DFR, because I compressed it on the DFR. I was running Windows 10, and then I decompressed it on Windows 11. It seemed fine.
So when you're reading it, you decompress it, or do you read the actual compressed file?
No, so I uncompress it from the zip folder, and then I get the histograms. So I never get the original signal data back. Like I only have the histograms, but the histograms are representative enough of the original signal data that I'm able to get useful information out of it.
So orchestrating all of this, is it all like shell scripts and whatnot?
It was just it was a scheduled thing. So like I went into on the DFR, I went into like Windows, and I could set scheduled tasks to run. So then just every single hour, I just scheduled this to run. And then at the end of the day, I'd schedule a task to go into a specific folder based on the day. So I'd have like the folder name would be that date, and then I'd just say, okay, compress this folder, and then return a zip file that has the same name. So then after a certain amount of days, I could just come in and pull the zip data out.
That part of it, is that manual, or is from that point forward also automated?
You could automate it. The issue is the security around it. That was the
Because
other.
it's all the devices.
It's locally on the edges.
Yeah. Okay.
On the edge devices. So we're treating the DFRs as edge devices. So we're doing edge compression and edge prediction, but then there needs to be a way to securely get that information back to the headquarters for like secure transfer and then secure storage.
Gotcha. And they're not connected to the internet.
No, they have their own private telecommunications line, but that can still be ingressed. So the power distribution grid is the most commonly attacked critical infrastructure, like by far. If you can take out someone's power, then like they're blind.
I mean, when they upgrade those i5s to something better, I mean, potentially you could save even more time.
Theoretically, but we prove that they don't need to, unless they like die.
Well, that'll happen.
Yeah, but they do downclock those i5s, so they're not.
So out of the $100,000 budget, I mean, they just write a check then to you for the remainder of.
Well, it paid for my.
Dr. Ty, yeah.
Yeah, well, it paid for my master's degree and my first year of PhD study. So
There you go.
Nice.
I did get something out of that.
There you go.
So you want your degree paid for too. Not big shoes, but maybe they'll be a little loose. And grow into them, but it's really cool stuff. Okay.
That's enough school for me.
I said that after my undergraduate.
You did.
I didn't bother saying that after my master's. I was like, who am I kidding?
But you had to move out, though, of your mom's place.
Yes. Yeah. Hey, didn't you move back in?
I did not. Well, kind of. It's
Okay.
father-in-law.
Okay.
Shots fired.
You won't hold this on the recording.
Yeah. Bernardo, editor.
I guess. Easter eggs, for fun. For everybody.